All right, guys, we're going to get started. This is 7.1, the mole. The learning goal is to use Avogadro's number to determine the number of particles in a mole. So the best part about this video is that you can pause, rewind, replay sections while you're writing, so everyone can move at their own pace. So people that like to write everything down have the time to do that. People that like to only write down certain things have time to do that. And so everybody can move at their own pace while still getting the notes. So go ahead and make sure you have that learning goal down, and we're going to move on to the next slide. All right, so the mole. The mole is an amount, okay? So think about things like a dozen. A dozen is 12. A case, if you were to pick up a case of soda, it's 24 cans. Avogadro's number is the same kind of thing. It's an amount of something, and so if you have, and it's called the mole, so if you have a mole of something, you have 6.022 times 10 to the 23rd of that object. Why is it such a big number, 6.022 times 10 to the 23rd? That means it has 20 zeros after that. It's really big because atoms are really small, so it takes a large number for us to weigh them and use them in a calculation, in a chemical reaction. So the mole is a quantity, just like a dozen or a case, and the number is Avogadro's number, named after Avogadro, and it's 6.022 times 10 to the 23rd. So knowing how to use this number in scientific notation is going to be really important in this unit. All right, so a mole, Avogadro's number, it's a unit that represents the same number of particles as there are carbon atoms in 12.01 grams of carbon. So that's kind of how we decided what it was. And then you can have a mole of any element, and that means that you have 6.022 times 10 to the 23rd atoms of that element. So if I have a mole of carbon, I have 6.022 times 10 to the 23rd carbon atoms. That's how many atoms there are. That's a whole bunch. If I have a mole of gold, I have 6.022 times 10 to the 23rd gold atoms. So 1 mole is equal to 6.022 times 10 to the 23rd of whatever you're counting. In these examples, it's atoms, but it doesn't have to be. So if it's an element, you have that many atoms. If we have molecules, you can have that many molecules. If you have an ion, you can have 6.022 times 10 to the 23rd ions. For formula units, you can have that many formula units. You could have a mole of Miss Lubinsky's, meaning you would have 6.022 times 10 to the 23rd of me. That would be a lot of me's. But you could have a mole of anything. You'd have a mole of eggs, and you'd have a whole ton of eggs. You could have a mole of footballs. You could have a mole of cheerleading shoes. Okay? Lots and lots of things in 1 mole. And remember, you can pause this, write all this down. You can stop at any time. All right. Why do we care about moles? Well, it's really useful for a conversion factor. So Avogadro's number, that's 6.022 times 10 to the 23rd, and yes, you are going to have to memorize that. It can be written as an equality, and you can get 2 conversion factors out of that. So the equality is that 1 mole, okay, is equal to 6.022 times 10 to the 23rd particles, whatever we're talking about, atoms, molecules, ions, formula units, that's how many of those 1 mole is. And so our conversion factors are written as fractions. So 1 mole is the same as 6.022 times 10 to the 23rd. And if you're trying to do it the other way, you can put the 6.022 times 10 to the 23rd in the top and the mole in the bottom. These conversion factors are going to be super, super useful because we're going to try and count how many particles are there in 1 mole of this, and you'll have to use these conversion factors. All right, so how do we use that to convert? Well, we use it to convert the number of moles of a substance to the number of atoms. So here's an example, and you're going to want to write this down. How many copper atoms are in half a mole of copper? All right, so we're going to have to use cups for these problems. So I have my handy dandy whiteboard here. I'm going to show you how to do these problems. Okay, so first starting with our knowns. Okay, what do we know? Well, we know that we have half a mole of copper. So I'm going to write down 0.5 mole of copper. Okay. And then I also want to know, what is my unknown? What am I looking for? And the question is, how many atoms? So I'm going to write, I need blank amount of atoms. Remember, you can pause this at any time. You need to write it down. The plan, I'm going to have us do our plan for these as the conversion factor, so the fraction. So I've got moles, and I need to go to atoms. So if I'm trying to get rid of moles, moles needs to go in the bottom. A conversion factor should be written as a fraction. So I should have 1 mole in the bottom, because that's what I'm trying to get rid of. And then atoms, because that's what I'm trying to get to, should be in the top. Well, how many atoms are in a mole? Avogadro's number, 6.022 times 10 to the 23rd atoms. So my plan is that conversion factor right there. Does that make sense to everybody? All right, so finally we set up our solve, and these are going to be t-charts because they're conversions. So in the top left, you put your known, 0.5 moles. Set up your t-chart like this. We're going to put moles down the bottom. You're just going to use that conversion factor, 1 mole. And then on top, you put 6.022 times 10 to the 23rd atoms. Make sure you've got those moles and those atoms on there so you don't get confused on units. Then we can cancel moles. We're left with atoms. You multiply across the top, 0.5 times 6.022 times 10 to the 23rd. That's going to give us 3, as you can see right here in the notes, 3 times 10 to the 23rd. 3.0, use your significant figures, okay? There are 2 sig figs here, 3 or 4 sig figs here, so we can only have 2 in our answer. So that's to be 3.0 times 10 to the 23rd copper atoms in half of a mole. Now some of you are like, did I really have to do all that work? Because clearly half of a mole is going to be 6.022. Yes, you have to show your work because they're going to get more complicated. Yay! All right. All right, so Avogadro's number converts the number of molecules to moles. So before we were doing atoms and moles, but we can also do molecules. So how many moles of CO2, carbon dioxide, are in 2.5 times 10 to the 24th molecules of CO2? We're going to use cups again, okay? Okay, so my known is, I know that I have 2.5 times 10 to the 24th molecules of CO2. So my known is 2.5 times 10 to the 24th molecules. You must know that molecules, the word molecules, okay, that's all the molecules, and MOL, if you abbreviate MOL, that's moles, not molecules. So my unknown is how many moles. So I'm going from molecules till moles. Why did I not have the E? Because I'm abbreviating it. My plan, come up with a conversion factor, a fraction. So I'm trying to get molecules in the bottom so it'll cancel out. So I'll put molecules down here and a mole up here. Mole's always the big one, right? So I have 1 mole and I have 6.022 times 10 to the 23rd molecules. It takes lots of molecules to make up 1 mole. So that's my conversion factor. Just make my t-chart for my solve. So I'm going to put my known up here, 2.5 times 10 to the 24th molecules. T-chart. Okay, put your known in the top left corner. Then I need to put my conversion factor in. So I've got 1 mole up top, 6.022 times 10 to the 23rd molecules down here. Cancel out the molecules. I'm going to have to divide those, and I'm going to have to know how to do this in my calculator. So let me find a calculator really quickly. Okay, so I'm going to divide 2.5 times 10 to the 24th, use parentheses, 2.5 times 10 to the 24th. Okay, put that in parentheses. That divided by Avogadro's number, and use parentheses again, 6.022 times 10 to the 23rd. Okay, see how all of that is in parentheses? This is 6.22 times 10 to the 23rd equals 4.15. Got to look at sig figs, so I had let's see, 2 sig figs here and 4 down here, so I can only have 2 in my answer. So it should be, or no, this is 2.50, I'm just being lazy. Just kidding, there's 3 sig figs there, I just forgot the 0. So 3 sig figs will give me 4.15 moles of CO2. Okay, cool beans. You need to look through that again if you don't understand what I did. Go ahead and pause and go back. Okay, so learning check. The number of atoms in 2 moles of aluminum is, so we can do our cups. We can go through all of that. So I'm going to go ahead and do that here. So my known is 2.0 moles. My unknown is how many atoms. Plan, well, I need to get rid of mole, so I'm going to put mole in the bottom. And I know that 1 mole is 6.022 times 10 to the 23rd atoms. All right. So then I'm going to set up my T-chart, 2.0 moles times 1 mole in the bottom is 6.022 times 10 to the 23rd atoms. You do 6.022, that's going to get you around 12, right, times 10 to the 23rd, or 1.2 times 10 to the 24th. So C is the right answer there. All right, so how can we use these in a chemical formula? Well, in a chemical formula, you know, the subscripts tell you how many atoms are in of those. So in NH3, you have 1 nitrogen atom and 3 hydrogen atoms. So you know that's the relationship, right? Well, that also tells us the number of moles. So you have 1 mole of nitrogen for every 3 moles of hydrogen. So subscripts help us not just know the atoms, but the number of moles. Aspirin, C9H8O4, you know what aspirin's used for, has the chemical formula here. So we can look at the fact that in a molecule of aspirin, you have 9 carbon atoms, 8 hydrogen atoms, and 4 oxygen atoms. And in a mole, okay, and remember, a mole is an amount, so think of it like a dozen. And a mole of aspirins, you have 9 moles of carbon, 8 moles of hydrogen, and 4 moles of oxygen. Okay, so we can make conversion factors. Remember those conversion factors, they're just fractions. So 9 moles is 1 mole. There's 9 moles of carbon and 1 mole of aspirin. In 1 mole of aspirin, there's 9 moles of carbon. You can write them either way depending on what you need it to be. So let's use that and figure out how many moles of carbon are present in 2.5 moles of aspirin. Okay, so starting with our cups, we know that we have 2.5 moles of aspirin. 2.50 moles. They want to know how many moles of carbon. So I'm looking for how many moles of carbon. Write aspirin up here. My plan, I need to figure out the conversion factor between a mole of aspirin and a mole of carbon. So I want the moles of aspirin in the bottom. So in 1 mole of aspirin, what did we say? We can go back a slide. In 1 mole of aspirin, I had 9 moles of carbon. So I can put 9 moles of carbon. That comes from those subscripts. So this is 9 moles of carbon and 1 mole of aspirin. And then that's our conversion factor, so we can just draw our T-chart. So we have 2.50 moles of aspirin. So I can put in 1 mole of aspirin down here, so that those will cancel. Then I have 9 moles of carbon. Okay, so these two will cancel. I'll just have to do 2.50 times 9. Pull up my calculator. So that's 22.5 moles. We got to convert it to only 3 sig figs because that's how many we have in 2.50. Oh, that is 3 sig figs. Awesome. So 22.5 moles of carbon is how many we have in there. Okay. Okay, so the last learning check is to find out the number of moles of sulfur in 1.8 times 10 to the 24th atoms of sulfur. So I'm going to let you do that one in your notebook and have me come around and check. Let's make sure you got it right. All right, peace out. Bye.